Hello, everybody. It's me, Mr. Salt, and we're here going to be doing Everyday Situations 1, 25.2. All right, number 25.2 in Algebra 1 Regents, Everyday Situation. And right here are the documents you need, and hopefully, this video that I'm making right now will be right here too. Okay, so there's basically two documents here. One looks like this. All right, that's the first document. All right, you'll be reading off this document. This will be like where you get your situations from, and you'll be doing the assignment on this document here, right there. Okay, so here's what I need to do. I need to open up this Word document. It's functions and everyday situations, 25.2, and then I'll open this one over here. And so here's your task. You're going to read the situation, take a look at what x equals, what y equals, and then identify some pieces of this situation, all right? You're going to identify the function family, which graph it belongs to, which table it belongs to, and where the missing entry on the table is. Let me walk you through this first one with the plumber. Pardon me. Okay, the plumber. A plumber charges a fixed fee for coming to your house, then charges a fixed amount per hour on top of this. All right, I'll read it one more time. A plumber charges a fixed fee. What's a fixed fee? A fixed fee is like they charge you $50 to even show up, right? Like, oh yeah, we'll come out by, but it's gonna be $50 for for us just to like stop by for even 1 second, and then we're gonna charge, let's say, $80 an hour for every hour it takes us to fix your problem. Okay, so that's what's going on here. A plumber charges a fixed fee. We don't know what that is yet, but oftentimes it's between $50 and $100 for coming to your house, and then charges a fixed amount per hour on top of this. And plumbers charge rates anywhere from $40 an hour to $120 an hour, something like that. So you got to think, what function family would this belong to? Maybe you want to pause me, think about it. It's really good if you do pause me, because that thinking time, sometimes you just need that thinking time. Okay, well, let's see. If it was quadratic, we would see the price the plumber would pay might go up, and then it might come back down. Could the price come back down? No, that's not going to happen. It's just going to keep going up, right? This plumber is going to, the more hours it takes them to, you can't see my finger. The more hours it takes them to do the plumbing job, the more you are going to have to pay, right? This graph just keeps going up. So we're looking at a linear function here, right? And why? So it can either be linear or exponential. Why do I say linear? The fixed amount per hour. What's fixed amount per hour? It means it's the same amount every hour. The same amount every hour is added to the cost, right? A fixed amount is added to the cost, right? And exponentials, what do? Exponential functions multiply and divide the same amount every time, and linears add or subtract the same amount every time. All right. So because we're adding a fixed amount, we should be thinking linear. All right. So now that we've figured linear, we go over here, we'd say, oh, it's going to be linear. All right. That's the function family it belongs to. So linears are going to add or subtract the same amount every time. Exponential situations are going to be multiplying or dividing the same amount every time, like doubling every hour or halving every hour. That's all exponential. Quadratics are something that's going to go up and come back down, or something that's going to go down and go back up, right? You're going to have a U shape, either a smiley shape U, or you're going to have a frowny shape U. And then an absolute value function, I don't know if we have any of these, but are going to have that V shape. They're also going to go down, go back up, or come up and come back down, but they'll have that V shape, and you can distinguish those that way. All right, we need to determine the graph. Determine the graph. The graphs are over here. So you scroll down past these situations, and here are my graphs. So what am I looking for? I'm looking for a graph that is linear, that is going up. All right? Can you see anywhere graphs anywhere that are linear and going up? All right, I'm seeing this is linear, but it's going down. That's curvy, that's exponential. That doesn't work. That's kind of linear, but it's going down. Here we have a linear going up, but this doesn't fit. Can you think why this one doesn't quite fit our situation? The plumber charges a fixed amount just to show up, and then they charge a fixed amount per hour. Why does this graph not work for that? Maybe you want to pause me, think about it, come on back. All right, it's because this graph starts at this point right here. It starts at 0, 0. So this would be like if there was no fixed amount for them to show up. We need our line to show up, to start somewhere on above this, right? It needs to be like start here and go up for this to work, because that starting up higher represents that fixed amount we get charged for, just for them to show up, just that $50 just for them to show up. That means this line's going to start not at 0, it's going to start at 50 or 100 or whatever they charge us that fixed amount. So we're looking for a linear that starts right there. Right there. Okay, looks like this plumber is charging $60 to show up, right? Because I see the line goes right through the 60. So this plumber charges $60 to show up. And let me see, after 1 hour, how much have they charged? They charged, I think it's about $100. I think it's about $100. So this plumber is charging $40 an hour. That's a very affordable plumber. This plumber's only charging $40 an hour. All right, that's a very affordable plumber. Let me get that guy. Let me get that guy's number or that gal's number. All right. All right. So that's kind of how it's going to go. Let me just read these to you, and we'll think about them. B, cycling. Oh, so let me go back. This graph here was G2. So I'll go over here, and I would put G2 in for the graph. All right, and now we're going to look for a table next. A table. So let's go back. We're looking at these tables. And again, we're looking for a linear function. It should start at 60, and it should progress up the same amount every time. Okay. So I'm looking for anything that starts at 60. I don't see anything that starts at 60. So then I'm going to look for, oh, wait. I do see something that starts at 60 right there. And time where X is 0, Y is 60. I think this is our table. So now it'd be probably table T3, if that's the one we're picking. T3 goes right there. And we got to figure out that missing entry. Well, if this is 60 and I have this gap, I need to figure out what is it counting by. So let me look over here instead. 140, and it jumps up to 180, and then it jumps up to 220. Can you figure out the sequence? How are these changing? 140, 180, 220. Maybe when I grab a calculator, do some subtraction, like 220 minus 180. Figure out what that is. And do 180 minus 140. Figure out what that is. Pause me and see if you can do that. All right, now you pause me, you unpause me. So 220 minus 180 would be 40. All right, and then 180 minus 140 would be 40 again. So what's happening here is it's going up by 40 each time. So all we got to do to find this missing entry here is add 40 to 60. All right, add 40 to 60, and then you can put in the missing number in your table. The first one's already done for you. All right, and that's the deal. You go through these situations and do that 10 times, and you're good. Okay, let me just read these so you get an idea of the situation, because I think the hardest part is really thinking about what family it belongs to. I think that's the hardest part of these. B, cycling. A cyclist travels along a direct route from town A to town B. X is the distance of the cyclist from town A in miles, and Y is the distance of the cyclist from town B in miles. So think, what function family would this belong to? A cyclist is traveling along a direct route from town A to town B. Direct means they're traveling in a straight line, right? And the graph is going to be a relationship between how far away they're getting from town A and how close they're getting to town B. So if you think about that, the farther away they get from their town A, the closer they're getting to town B. And if it's a direct route, there's going to be a direct relationship. Well, a direct relationship is going to be a straight line. And what function family has straight lines? All right, so maybe you have the function family already. You put the function family in here, right there. Now we're looking for a graph. We're looking for a graph that's a straight line. And we're not going to use this one. This one was the plumber one. Now we do have some blank graphs, so sometimes there might be some graphs that aren't represented here. We might have to graph those or think about what they would look like. So as I get further away from one thing, I'm getting closer to the other. So as I get further away from the one town, I'm going to get closer to the other. So sometimes, as I was just thinking, I paused it because as I was thinking, sometimes it's best to decide. We're looking for linear, but we don't know if it's going up or down, right? We're looking for a direct relationship. So sometimes it's best just to take out a piece of paper and sketch a graph. Now I got some handy graph paper here, and I just did 1 through 10 here and 1 through 10 here, just because all I want to do, I don't need to have the correct numbers right now. I just want to have the correct shape of my graph. I need to think, like, do I want to start my graph over here? Is that where I want to start it? Because then if I start here and I go like this, I go straight line this way, what ends up happening is the further I get away from the one city, also the more my numbers increase this way. So if I draw a line starting here that goes that way, then when I'm going to end up like, say, like this G7 right here, the further I get away from the one city, the further I'm also getting away from the other city. So this graph right here doesn't quite work. Let me kind of just show you what I'm thinking. If I'm 0 miles away from Rochester, right? If I'm 0 miles away from Rochester, let's say I'm 100 miles away from Buffalo. So I'm going to put a point right there. After I get further away from Rochester, I'm going to have to put 20, 30, 40. I'm going to change some of my numbers here. All right, I'm going to put some zeros. 100, 100. Okay. So as I get further away from Rochester over here, I'm going to get closer to Buffalo if I'm traveling a direct route. So what I should have is a linear function going down. Let me kind of show you how that works, right? This is where I start. I'm 100 miles from Buffalo. I'm 0 miles from Rochester. As I get 10 miles more away from Rochester, I'm getting closer to Buffalo. As I'm getting further away from Rochester, I'm getting closer to Buffalo. So this is so hard to do when I'm like this. So in this graph, I'm going down. So I should see something like I'm going down. This could be it. This could be it. What else? Is there any other linears going down? No. So we have to decide whether it's this one or this one. Okay. And how do we decide? Remember what the difference is. A line means it's a continuous function. Dots mean it's a discrete function, right? Continuous means when you can continually divide up and make the units smaller, and that makes sense. Discrete means you can't cut the units up. They only make sense as discrete units, okay? So for instance, while I can travel 10.5 miles, that makes sense. That's fine. I can do 10.5 miles. I can't teach 10.5 students. What would that even mean to teach 10.5? What's the 0.5 student? Like what? No, I can only teach whole people, whole human beings, right? So how many students I can teach would have to be a discrete function because we can't we can't have fractions of a student. That doesn't really make sense in the situation. But fractions of a mile, you can divide up a mile into smaller units and into fractions and decimals of a unit. So that works. So this is going to be our function right here, G10. All right. So now we have to go to the table and we're looking for something that starts high and continually goes low the same amount over time. Do you see anything that starts high and goes down the same amount every time? There's 16. This one starts high and it goes low, but is it going down the same amount every time? It goes down by 800, goes down by 400. No, it just changed. It changed. The rate of change changed. We need to look for something that's going down the same amount every time. All right, I'm going to leave you to it at this point. All right, I'm going to leave you to it to figure these out. We did the graph, we did the table. Oh, finding the missing entry. No, I'm going to leave you to it. All right, That's the assignment, and that's what I want you to work on. Give this a shot.